Hello again. Today we're finishing up our discussion on tests for convergence and divergence of series, and we're going to talk about series that have error terms associated with them. So let's get started. Before we talk about any of those tests, we need to talk about what it means to have an error term associated with a series. So a lot of these series, if they do converge, then there is a sum that those series add up to. But for a lot of these series, these different types of series, I don't have a formula to figure out what it is. So I can't really figure out what the infinite sum is, even though I know it exists and that the series does not go off to infinity. So if I can't figure out what the sum actually is, I can come close to it by adding up the first few terms, the first 3 terms, the first 5 terms, whatever. However many terms there are that I'm adding together, I'm going to call that the partial sum. So if it's 3 terms, it's the third partial sum. And if it's 5 terms, it's the fifth partial sum. In general, it's the nth partial sum of the series, meaning that I'm not adding up all the terms. But if I only add up some of the terms, obviously that's not the exact same thing as the infinite sum because I've left off the rest of the terms. So there's going to be an error. There's going to be an amount that I'm off by, and that amount will be the infinite sum s minus the partial sum, that s sub n. And again, I don't know how big the infinite sum is, so there's no way of knowing how big the error is. So the best I can do is maximize the error. I can say that the error is at most this amount. And what that does, if I combine that with my approximation, I can come up with a range of possibilities for what the infinite sum could be without actually knowing what it is. So I'm going to talk about 2 tests that have this type of error term associated with it. The first is going to be the integral test. So let's suppose that I have a continuous positive decreasing function f of x for all x's greater than or equal to 1, and that function has an integral from 1 to infinity. If the integral from 1 to infinity converges, then the sum of the series that I can create using points in that function, that also converges. And also if the integral diverges, then I can similarly say that the series diverges as well. So here's an example. I'm going to show that this series, 1 over n squared times the cosine of 1 over n, I'm going to show that that converges. And to do that, I create a function that looks very similar to it. It's 1 over x squared times the cosine of 1 over x. Now that is continuous, it is positive, and it is decreasing for x's 1 and higher. So it does qualify for the integral test. So I'm going to find the integral of this, but remember when I have infinity as one of my endpoints, I can't plug in infinity. So I change that infinity to a b, and I find the limit as b approaches infinity. Well, if I integrate this function that I've created, I get the negative sign of 1 over x. I'm going to evaluate that at 1 and at b, and I'm going to find the limit as b goes off to infinity. That will give me the negative sign of 1 over b plus the sign of 1 over 1. As b goes off to infinity, the 1 over b approaches 0. And so I get negative sign of 0, which is 0. And sine of 1 over 1 is just the sine of 1. So my final answer is the sine of 1. That is the area under that curve from 1 to infinity. That is a finite number, so that means that the integral does converge. That also means that the series that the function was based on converges as well. Okay, so let's talk about why this test actually works. Why can we say that the series does whatever the integral does? Well, let's draw a quick picture. I'm going to draw a picture of what a series would look like as a bunch of rectangles. And for each of those rectangles, the width is going to be 1, and the height is going to be the value of that term in the sequence. So the first rectangle is going to have a height that's equal to the value of the first term. The second rectangle will have a height that's equal to the value of the second term, and so on. So that means that the total area of all of those blue rectangles is going to represent the sum of the series. I've got dots on there to represent 1 for the first term and A1 for the value of the first term, 2 for the second term and A2 for the value of the second term, and so on. I do that so that I can create a function f of x using the terms in the sequence as points in that function. And what I'm going to do, since this is the integral test, is I'm going to show you what the integral would look like. The area under that curve from 1 to infinity. That's part of what the integral test requires. So that orange area is going to be the area under the curve. So let's talk about how the area under the curve compares to the area of the rectangles. If I just look at the second rectangle, the third rectangle, and so on, and I ignore the first rectangle. All of those rectangles, the sum of those rectangles is the sum of the series, and that is clearly going to be less than the area under the curve. So if the area under the curve is a finite number, then the sum of those rectangles, ignoring the first one, the sum of those rectangles is going to be a finite number as well. And in fact, it's going to be smaller than the area under the curve. All I have left to do is add on that first term that I've been ignoring, but that's finite as well. So if I have a finite sum and I add on one more number, that's still going to be a finite sum. So that means that if the integral converges, then the series converges. Now let's show the second part. I'm going to move the rectangles one place to the right. It's still the same sum, but it's just moved to a different place. Now let's assume that the area under the curve, that orange area, is infinite. It diverges. It does not approach a constant. Well, if that area under the curve diverges, then the sum of all of those rectangles, which is clearly bigger than the sum of the area under the curve, because all of those rectangles are higher than the curve. The sum of those rectangles is going to be bigger than an infinite sum, which approaches infinity. So if the area, the orange area, is infinite, then the area of the blue rectangles must be infinite as well. In fact, it's going to be like a bigger infinity if you can consider that. So if the integral diverges, then the series diverges as well. All right, so that's just a quick explanation. It's not a formal proof, but it helps you see why I can say that the series does whatever the integral does. So let's use this to talk about the harmonic series, and this is one that puzzles a lot of people. Why would the series of 1 over n diverge? Let's talk about that by using a function 1 over x that looks similar to 1 over n, and we're going to integrate that from 1 to infinity. Remember, I can't integrate at infinity, so I make my top limit b, and I let b approach infinity. Well, the antiderivative of 1 over x is natural log of x, and I'm going to plug in 1 and b, and I'm going to let b approach infinity. So that gets me the natural log of b minus the natural log of 1. The natural log of 1 is 0. So all I'm left with is the natural log of b. But as b goes to infinity, if you remember what the natural log function looks like, as b goes to infinity, the natural log of b goes to infinity as well. There's no bound to it, to how high it's going to go. So that integral does diverge. And so according to the integral test, the series diverges as well. All right, so how do I approximate the area for the integral test? Once I know that a series converges by the integral test, then how do I know what the error term is? So let's say, for example, that I only wanted to add the first 3 terms to approximate the sum, the infinite sum of the series. Well, what I could do is I could say that the error would actually be the sum of the remaining terms, all of those rectangles after the third one. But obviously I can't add all of those together. So what I do is I look at the area starting at x equals 3 and moving on down. And since I know that that is going to be a finite number, I can say that the sum of the rectangles will also be a finite number. I also know that the orange area is going to be bigger than the sum of the remaining rectangles. So what I can do is I can say that I don't know what the sum of the rectangles is going to be, but I do know that it is less than the area under the curve from 3 to infinity. And in general, if I stop adding terms at the nth term, then I'm going to find the integral from n to infinity. So if I stop at the 5th term, I'm going to take the integral from 5 to infinity, and so on. All right, so for example, let's estimate the sum of this series by adding the first 3 terms. So the first 3 terms, I just plug in 1, 2, and 3 into that formula, and I get those 3 terms, which add up to 0.8. Okay, now I need to maximize the error. Well, since I stopped at the 3rd term, I'm going to integrate from 3 to infinity of that function. As a limit, remember I change infinity to b, and I take the limit as b goes to infinity. And I find the antiderivative. The antiderivative of that function is the arctangent of x. I'm going to evaluate that at b and at 3, and let b go off to infinity. So the limit as b goes to infinity is going to be pi over 2, because remember the tangent of pi over 2 does approach infinity, so the the arctan of something that approaches infinity approaches pi over 2. And then the arctan of 3 is just the arctangent of 3. And that's a constant as well. That's approximately 0.322 if you type that into a calculator. So that's going to be my error. It's not actually the error, but I know that my error is less than that, which means that my approximation of 0.8 is off by less than 0.322, so that I know that the actual sum of the series is somewhere between 0.8 and whatever I get when I add 0.322 onto 0.8. So the sum of the series is somewhere between 0.8 and 1.122. All right. Now let's talk about the alternating series test. This is the last series that we're going to talk about in this unit. So if I have an alternating series like that, then if the absolute value of the n plus 1 term is less than the absolute value of the n term, so if every term is less than every term that comes before it, and if the terms eventually approach 0, then I can say that this series is convergent. So there's really only 2 requirements there to show that a series is convergent. So I need to show that this series is convergent. Okay, well, if I look at the nth term, that is 1 over n, and if I look at the n plus 1 term, that's 1 over n plus 1, which has a slightly bigger denominator, which means that the fraction is slightly less than 1 over n. So clearly the n plus 1 term is less than the n term for positive n's. Remember, I'm ignoring the sign when I do these comparisons. That's why the absolute values are there. And obviously, as n approaches infinity, then 1 over n is going to approach 0. All right, so both requirements have been met. That means that the series converges. All right. When we're talking about alternating series, we need to talk about absolute convergence and conditional convergence. So the difference is if something is absolutely convergent, that's related to absolute value. So basically, if I ignore the fact that terms are positive and negatives, and I just look at the positive version of each of those terms, meaning I take the absolute value of those terms. If I drop the positive and negative and treat all terms as being positive, and that series converges, then I say that the series is absolutely convergent. Okay. So I can say that this series, -1 to the n over n squared, is absolutely convergent because if I take out all those negative 1s and I'm just left with 1 over n squared, I know that that is convergent because it's a p series where p equals 2. Okay. The other thing is conditionally convergent. If a series is convergent by the alternating series test, but it's not convergent when I drop all the positives and negatives, then I say that that series is conditionally convergent. It's only convergent if I keep the pluses and minuses with every term. If I drop them and make them all positive, then it's not convergent anymore. So the condition is that the pluses and minuses have to stick around with each of those terms in order for that series to be convergent. Okay, so again, I can look at -1 to the n over n. That's conditionally convergent because if all the terms are positive, we've got the harmonic series, which is not convergent. But once I put the -1 to the n's back in there and alternate sign with each term, then the series does become convergent by the alternating series test. So that's the difference between absolute convergence and conditional convergence. Now let's talk about approximation errors with an alternating series. So let's say I have this sum that is the sum of an alternating series, and it satisfies both conditions of the alternating series test. Then the error is just the term after where I stopped counting terms. So in other words, if I wanted to approximate the sum of an alternating series test by just looking at the first 3 terms, then the error would be my 4th term. The error is always going to be the n plus 1 term, where n is the term where you stopped adding terms together to approximate the actual sum. Okay? All right, so for example, let's say I want to know how many terms of that series are necessary to find an approximation that is accurate to within 1/1000th. All right, so we've talked about that this series converges absolutely, which means it converges. So the error term is just going to be the next term. And so that's going to be 1 over n plus 1 squared. All right, I need that error term to be less than 0.001 or 1 over 1,000. So if I flip both sides over, that means I flip the less than to be a greater than, and I get n plus 1 squared to be greater than 1,000 over 1. If I solve that, I get that n has to be greater than the square root of 1,000 minus 1, which is 30.62. And obviously I can't have a 30.62 term, so I have to go to the next one, and that would be 31. So I need to take 31 terms of this series in order for it to be close enough to the actual sum of the infinite series so that I'm only off by less than 1/1000th. All right, so why does this work? I'm going to show you another picture of why this works. Why do I only need the next term in order to maximize the error between my partial sum and the actual infinite sum? So remember, this is an alternating series. This rule only works for alternating series where the terms go positive, negative, positive, negative. So let's just arbitrarily say that the next term, after I've done my partial sum, let's say that that next term is positive. Well, the term after that is going to be negative. And so if I add those two together, that's actually going to be less than just the next term by itself. That's going to be less than just the green rectangle by itself. And then if I keep on adding positive and negative terms, the overall sum is never going to be as big as that first next term that I found. So the next term is actually going to be bigger than any other approximation of an error that I could find. All right. So here's another example. Let's find a range of values for the sum of -1 to the n over n factorial. And we're going to use the sum of the first three terms as an approximation. First, we need to check for convergence. Is the n plus 1 term less than the nth term? Yes, it is. Does the nth term approach 0 as n approaches infinity? Yes, it does. And so what I do is I look at the first three terms. The first term is going to be negative, so it's going to be -1 over 1 factorial. The second term will be 1 over 2 factorial. And the third term will be -1 over 3 factorial for a total of -2/3. So that's just an approximation of what the infinite sum would be. So the error then, since I only went to three terms, the error is going to be the fourth term, which is -1 to the fourth over 4 factorial. That is +1 over 24. Okay, so the sum is such that it is somewhere between -2/3 and -2/3 plus 1/24, whatever that is. Well, that's -5/8. So the actual infinite sum is somewhere between -2/3 and -5/8. And if you want to look at decimals, it's somewhere between -0.6666 repeating and -0.625. So that's a pretty small range. So I've gotten it pretty accurate there. All right, so this is our final summary of my convergence tests. I've looked at all of the tests that we need to know for this unit, and I've added the last two in there, the integral test and the alternating test. So feel free to copy this down, take a picture of it, whatever you need to do. We will need to know all 8 of these. If you have any questions about this, please let me know, and I will see you tomorrow.